Okay, hi everyone. Welcome to my talk about the one-way to hiding lemma. I'm second some modifications. Okay, so the one-way to hiding lemma is a proof tool that we encounter in proofs of post-quantum security quite often. Yeah, the context, as I just said, is quantum-resistant public key primitives. Like this, turn on the sound. Is it possible?
Do you want the sound effect?
No, turn down the sound because I can hear myself and I'm feeling like this creates some Okay, sorry about that. So one-way to hiding is used to replace classical reprogramming strategies, and common use cases are CCA transformations as were used during the NIST competition, for example, the well-known Fujisaki-Okamoto transformation, but also block ciphers, message authentication codes, zero knowledge proofs, and authenticated key exchange. And to give a short outline and just get to the goal of this talk, I'll first give an example for a typical reprogramming use case we encounter in post-quantum security. Then I state the simplest version of one-way to hiding, that is also called original one-way to hiding. Afterwards, I discuss some extensions and improvements we have seen in the last few years, and then I'll conclude with a summary. And at the end of the talk, I'd be happy if you understood where and how one-way to hiding can be used and what the best known bounds are for specific scenarios. Okay, so moving forward to our motivating example, reprogramming use case. So what we're looking at now is a PKE transformation that I will call derand because it's a derandomizing PKE transformation. And this is a transformative step that is used in recent CCA transformations, like the Fujisaki-Okamoto transformation. And we also know this transformation as encrypt with hash. I think it was introduced by Belare. And what do we do? Yeah. So we take a PKE scheme and a random oracle G, and we construct a new public key encryption scheme that's defined relative to the PKE scheme and the random oracle. And what we do is to use the key generation and the decryption algorithm as is, but change the encryption such that encryption is done deterministically by using the hash value of the message as the encryption randomness. And in the random oracle model, there's a theorem that states that if the underlying encryption scheme is one-way secure, meaning it's hard to invert ciphertexts, then the resulting scheme is also one-way secure. And this is a scenario in which we will encounter reprogramming. So what I will do now is to sketch the proof. So on this slide, we have on the right-hand side an adversary aiming to invert the ciphertexts for the new derandomized scheme. And we want to construct a reduction that inverts ciphertexts for the underlying probabilistic scheme. And yeah, the adversary expects as input a public key and a challenge ciphertext C star, and will answer with a guess for the plain text M prime. And what we do now is to give a reduction that simply takes as input a public key and a challenge, forwards it to the adversary, and returns the same message guess as the attacker tries to exploit. And if we think about it, if we have a ciphertext C star that's an encryption of a message M, and A wins, then it has returned this message M, meaning that if A wins, B also wins. But the view of A is not perfectly consistent because A expects a deterministic encryption, whereas B obtained a random encryption. meaning that the reduction only works unless A has queried the random oracle on the challenge plain text. So what do we do there? What we do there is to give another reduction, which we call C. And C will receive the random oracle queries issued by A, store them into a list, answer via lazy sampling, and in the end it picks one of the queries at random and outputs this as its guess. And if A has queried the random oracle on the challenge plain text, this means that it must be included in this list, and hence C will win with probability 1/Q. And as the final result, we get that the advantage of A against the de-randomized scheme can be upper bounded in terms of the first reduction that just forwarded A's guess, plus Q times the advantage of the second reduction. Okay, now that we've seen the proof sketch, I will shortly discuss what the takeaway from this proof was. What we have used is that in the classical random oracle model, a particular oracle value is indistinguishable from random unless the random oracle was queried on the respective pre-image. And we also used that queries can be memorized by reduction and then used later, for example, to form the output. And in the QRAM, stuff becomes less trivial because we can't even say what it means that G of M was queried, because quantum random oracle queries are done in superposition. So in this scenario, for example, the challenge plaintext is hiding in a superposition. And also, as we have already seen, bookkeeping isn't completely trivial. And this is where original one-way to hiding comes into play. So the original version is intuitively, it's a quantum counterpart of random answer query. What we have here is that we have an adversary that's interacting with a random oracle G, and it obtains a particular pre-image or position, and either the random oracle value on this position or a uniformly random value. And we care about the difference between A's behavior in the first case and the second case. And to upper bound this distinguishing advantage, we will use an extractor that uses A's interaction with G to extract the pre-image. And how does it work? It picks a random I between 1 and Q, meaning it picks a random query that is issued by A. It runs A, but only until the ith query, then measures the input register of the query and returns the measurement result. So after the ith query has been issued, A is just aborted because we don't even need it anymore. And what original one-way to hiding states is that the distinguishing advantage of A in those two scenarios can be upper bounded in terms of the number of random oracle queries, this is Q, and the probability that the extractor answers with X. Now I will show you how we can apply this to the use case we have just seen. So here we consider one game I call G0, which is just the one-way game, where the challenge ciphertext is still a deterministic encryption of M. And the probability that A wins in game G0 is just the one-way advantage of A against the de-randomized scheme. In game G1, we use a probabilistic encryption, meaning that if A wins in G1, then the classical reduction we have just seen before, the reduction B, will also win. So what we already know is that the advantage of A can be upper bounded in terms of the reductions advantage plus the distinguishing advantage between those two games. And this is where we use one-way to hiding, because we can now define a one-way to hiding extractor, as we have seen on the last slide. It picks a random query to be measured, runs the adversary until this query measures the input register and returns the measurement result M prime.
There is a measurement on result M prime, but again, it's just a bit, right? So,
no, the distinguishing in the distinguishing game, the output of the distinguisher is B, a bit, but in the one-way game, the adversary is expected to answer with a plain text guess, right? And the extractor also did try to answer with the position on which the reprogramming happened. Mm-hmm.
Is value about the advantage thing due to being a search problem?
That's a very good question. That's a very good question, and you're spoiling the talk a bit, because there was a lot of research invested into the question whether we can circumvent the square root, and I get to this in a few slides. Mm-hmm. This slide, I mean?
So the question is, an adversary gets an input, output.
Mm-hmm.
Distinguish whether it's a g of x or a random
Uh-huh.
and it has an output g.
Yes.
And where the output g is
Yes.
example.
Yeah, and this is exactly the probability that the extractor will also measure x in the query, no? So the intuition is that the adversary will not be able to tell g of x from random unless it queries the random oracle. And this is what we will use, what we will exploit to give a reduction towards one-wayness. Oh, yeah, sorry. Yeah, true. Not used to those hybrid formats. Okay. Yes, we start here, I think. So what we've seen now is that we can upper bound the distinguishing advantage of A between those two games in terms of a new reduction. And this is good because now we are done and have a Q1 proof for the de-randomized scheme. But as a question a few seconds ago already hinted at, we might not be too happy with the bounds we are seeing, because the bound loses a factor of Q and we also lose a square root. So the result is not very tight. And also we are only considering a situation in which we only do one reprogramming, meaning that if we are in a proof scenario where we want to reprogram many positions, then we have to add another bound for each instance of the reprogramming. And also the game must know the position to be reprogrammed a priori. By that I mean before starting the adversary A. So the result is not applicable to proof situations where the reprogramming might also depend on the interaction with an adversary, like, for example, in proofs for signatures. And this is why there has been a lot of work on extending one-way to hiding to achieve tighter bounds or to generalize the scenario, some of which I will present to you for the next few minutes. So the first interesting result I want to explain in a bit more detail is the one by Ambainis et al. That's called semi-classical one-way to hiding, where we get a tighter bound in certain scenarios and are also allowed to reprogram on several positions. And there have been some tightness improvements that were achieved by smarter extractors, where we use a bit more quantum technique. And then also there have been two generalizations I wanted to mention. The first generalization generalizes one-way-to hiding to the compressed oracle model. And the second one allows for adaptively chosen positions. Yeah, but I will start with semi-classical one-way-to hiding. So it's still counterpart of random antiquary, but it's a bit more general. What we have here are two oracles, G1 and G2. They go from a set X to a set Y. And we consider a set S, that is a subset of X. And what we want is that G1 and G2 coincide everywhere but on S. We also consider an additional input string Z that will be the input to A. And the oracles, the set and Z, can have a shared distribution. And what we want to do now is to give an upper bound for A interacting with G1 or A interacting with G2, which means that we can reprogram the oracle on the whole set S. And to state the theorem that we will want to use, I will first have to introduce some notation. So first I wanted to...
The string C is that like a constant string or a very infinitely important string?
I'm not sure whether Z could be a quantum string. Let's just think of a classical string for now. But usually we run our adversaries in post-quantum scenarios on classical strings. So for our use cases, this is not too much of a limitation. Like think of a public key or something like that.
You could do a simple reduction and just put X because there's actually no complexity limitation. So if you have an algorithm that takes a quantum Z, you could just encode in Z a complete description of that quantum state and make a universal that produced this one. Because we need some information here to the theorem. So we could extend it. And the theorem doesn't say it.
So what Dominique just said was that since this is an information theoretical bound, we don't have any limitation on the complexity of Z, meaning that we also could replace that with a quantum bit string. But for the rest of the talk, we'll still just consider a classical string for ease of presentation. Okay, so to introduce some notation before giving the theorem, I will first explain what a semi-classical oracle is for a subset S. So this oracle is applied to a state that's held in an X register, meaning it corresponds to the input register of an oracle and an additional bit register. So for example, think of a base state X0 for some X in the set X. And the intuition is that the oracle flattens the state to a new state psi prime, such that it only contains elements of S, or such that it only contains elements that are not in S. So think of it as... Sorry, I'm not hearing you very well. Could you speak up? So that's just the input register to the oracle. So I'm just describing on which, on what the oracle is working. And I will make this more formal in just a second. Okay, so to describe what flattening means, because this is very informal, what we do is that we have this oracle act on, so I'm just describing how it works on a base state because it's a unitary and we can do linear completion. So what it does on a state X and B is that it maps X and B to X and B XORed with B prime if X is an S, and then measures the second register. And to give an example how this application would look, consider the set X just to be the set of a bit of bits, and the subset S is the set that contains 1. And let's say our state psi is 0 with probability 1/3 and 1 with probability 2/3, censored with 0. And now we want to see what the semi-classical oracle does to the state. Yeah. First, 0, 0 will be mapped to 0, 0 because 0 is not an S. And 1, 0 will be mapped to 1, 1 because 1 is an S. And afterwards, a measurement is performed, so the whole state will turn to 0, 0 with probability 1/3 and 1, 1 with probability 2/3.
Small question. Just to figure out the template. Assuming for example, we have the same 1/3 0, 0 and 2/3 1, 1, and then we'll have the outputs again 0, 0 and 1, 0. Am I right?
No, then we would have 1, 0, right?
Huh?
Then we would have 1 and 0 for the second state, no?
Yeah,
Because
yes. Is it 0, 0 for the first one,
Mhm.
still remain, and 1, 0 for the second? This we flip this.
yes. Correct. Okay, and what I will do now is to show how we can use those semi-classical oracles to define punctured oracles. So just recall that the oracle flattens the state to a state that has either 1 in the last register and only contains elements of S, or the last register is always 0 and the first state only contains elements that are not in S. And a punctured oracle G punctured by S, is defined as follows. Before we apply the oracle unitary UG, we will first apply the semi-classical oracle. And now we will define an event find. The event find is defined as the event that the second register switched to 1 during application of the punctured oracle, meaning that if find does not occur, the set S is effectively removed from the domain of the oracle because it's never queried there. And if find occurs, then measuring the X register of the state would always yield an element in S. Okay, now with this notation, we can finally introduce the theorems that are useful for us. So we still want to upbound the distinguishing advantage between those two oracles that only differ on a subset S. And the first theorem states that the distinguishing advantage can be upbounded in terms of the number of random oracle queries and the probability that find occurs if the adversary is run with access to the punctured oracle. But if we want to give a reduction, it might be that the reduction itself does not know the puncturing set. So it would not know how to simulate this punctured oracle. And also, we still have to find a way to use the find event to extract a desired pre-image in S. And this is where the second theorem comes into play. That states that this probability can also be upbounded in terms of the number of oracle queries and the success probability of the extractor that we've already seen, the one that runs A until a random query, measures the input register, and returns the result. There's also another observation. If the input of A is independent of the set on which we puncture, then the probability that find occurs can be upbounded in terms of the number of oracle queries and the maximum probability that an element is in S. Recall that S is a random set. So for example, if we have a set S that only contains one element that was sampled uniformly at random, then the bound would be 4q over the size of X, which is 4 times the classical bound for the same scenario. Okay, now I can show you how we can use semi-classical one-way-to hiding for our example use case. So again, we have this one-way game where C star is deterministically computed. We have this game G1 where C star is random. And we've already seen that the advantage of A can be upper bounded in terms of this reduction E that we have seen in the random oracle model and the distinguishing advantage between those two games. And this is where we now plug in one-way-to hiding in the semi-classical version. So what we do know is that we can upper bound the distinguishing advantage by this bound. And to make it more explicit, the probability of find is the probability that find occurs when A is run with the punctured oracle on M and has as input a public key and a random encryption. Now we still want to upper bound the probability of find, of course. So we could just use the query extractor as before, dealing the one-way reduction C prime. But that would mean that find loses another factor of Q. If the underlying scheme is even stronger, has a stronger security notion than one-way security, we will see that the upper bound can be improved quite a bit. Namely, if we assume in CPA security, meaning it's hard to tell which one of two messages was encrypted, then we can define a new event PR find prime, and it only differs from find in where we puncture, because now we will just puncture on another independent random message M prime prime. So the first observation is that the probability of this new event can be upper bounded by 4q over the size of the message space, because M prime prime, the set on which we puncture, is independent of the input of the adversary. So that's already nice, but we still have to upper bound the distinguishing advantage between find and find prime. And to this end, we can give a CPA reduction T that will just pick random M prime prime, random M, forward it to the CPA game, and use the ciphertext it gets as input to forward it to A and puncture on either of these messages. So what we have achieved is that we have now upper bounded the probability of find by a term relative to the size of the message space and the advantage of the CPA reduction. So the reduction itself doesn't lose the factor of Q. In conclusion, we have now seen a more general counterpart of random anti-query that has several advantages. First one is that we can reprogram on arbitrary many positions. And the second one is that we get a tighter bound if the reduction knows how to puncture, and we can upper bound the probability of find tightly. And what I want to present to you now are several improvements on the bounds with smarter extractors, as hinted at before. So the first version I want to show you is double-sided one-way-to hiding, and we'll see in a second why it's called double-sided. Again, we have those two oracles that coincide anywhere but on S and the input to A. And we still want to upper bound the distinguishing advantage. And the new bound we see here doesn't lose a factor of Q at all. And it is defined in terms of the success probability of an extractor that has access to both oracles at once. And the intuition behind the extractor is that it runs A on G1 and G2 in superposition. And since the oracles only differ on the particular desired pre-image X star, the adversary, when noticing the difference, will be entangled with X star, and to exploit this, we'll just add another additional register that will hold the information we desire, and I make this formula on the next slide. So first I'll explain what it means to run A on G1 and G2 in superposition. To this, I first define a new unitary I call U_sup for superposition G1, G2. And what it does, it takes as input registers the oracle input-output registers X and Y, and another bit register that indicates which of the two random oracles it is supposed to use. And what it does now is to map X, Y, and plus to X, Y, that takes as input the input-output registers of the oracle, an additional bit register, and another register that also corresponds to X. And the only thing it does is that additional XORing first register into the fourth.
Okay, this is not work. This is not work. It's just a
Yeah. Yeah. Yeah, just keep in mind that X is pushed into the last register conditioned on B. Okay, and now combining those two unitaries into one, we get an evaluate and swap unitary. And this we will now use to exploit our adversary in a way such that the desired pre-image will be extractable from the last register. So an observation we can make is that if we use this combined unitary on an input-output register and 0 registers in the end, then it will just evaluate the random oracle G1 on the first two registers, and the rest will remain 0. And if we apply it to X star, then the state will transition to a state where the last two registers contain 1 and X star with high probability. So I think we've already seen this before, that we can identify adversaries with oracle access to the random oracle G as a sequence of unitaries interwoven with random oracle unitaries. And our extractor now will do the following, and will prepare the registers for the adversary A. And two additional registers. The first register will just contain a 0 bit, and the second register will contain the 0 of the set X. And instead of running A interwoven with the oracle unitary, we will now run A interwoven with this evaluate and swap unitary. And at the end, we measure the last register and output the result. So this is how the extractor is defined, and that allows for a tighter bound, but only if the reduction knows how to simulate both oracles, because we will need both oracles during the evaluate and swap unitary. And another simplified, another extension of one-way-to hiding was given, and it was called the measure, rewind, measure approach. And I also give it a simplified.
So in the regular one-way hiding, the right-hand side of the equality of both.
Sorry?
So in the regular one-way hiding, the extractor works for both of them. I mean, not simultaneously, but it can work for both of them.
The original one-way-to hiding or the semi-classical one? I mean, it doesn't really matter. You can, so the right-hand side, the extractor for original one-way-to hiding and for semi-classical one-way-to hiding, it just uses one of those two oracles.
Yeah, but it can use any of those.
It can use any of those.
Yes. Here you said it uses both of them. But so is there a difference between the proof using both oracles at once? Like in what scenarios will it be difficult to simulate both oracles at once compared?
It might be difficult to simulate both oracles in scenarios where the adversary, our reduction, doesn't know the random oracle value, right? So for example, in the use case we've just seen, the reduction gets a ciphertext T star, and it's defined using randomness R, just uniform randomness. And now the reduction to be able to evaluate both oracles would have to define the random oracle G2 that maps M to this randomness that was used in the encryption. And since the reduction doesn't know the randomness that was used to define C star, cannot simulate the second oracle. Does this make sense? Okay. So
it might know neither of the two, right? The reduction might know neither the randomness nor M.
yeah, I mean the one oracle can just be sampled by the reduction itself.
Right. Yeah.
So it knows how to simulate G1 because it just.
That's right.
Yes. So the result is nice in the sense that it doesn't lose a factor of Q, but it's also not applicable generally. You really have to work a bit to make sure that it is applicable. Yes, and now I wanted to discuss another improvement that does not have a square root loss, and this is particularly interesting because after the improvement I have just shown you, there was a bit of a discussion whether the square root loss is unavoidable in the community. I also got this question a few minutes ago, and now we'll see that we can also give upper bounds that do without a square root at the cost of reintroducing the factor Q, the number of random oracle queries. And what we have here is that we still want to upper bound this distinguishing advantage. And now we upper bound it in terms of an extractor that is also run with access to those two oracles at once. And it will output a particular set of two elements I will discuss in a bit. And it succeeds if either one of those elements is contained in S. And the intuition behind the extractor we'll see, and the upper bound is that we can either extract from a random oracle query, or the distinguisher must have performed a distinguishing measurement. And this measurement already can be used to tell us a bit about the pre-image on which the reprogramming happened. So to define the extractor, as usual, it will pick a random index I that represents a particular query. And it will extract the first guess before the set by extracting a pre-image from the ith query using this evaluate and swap unitary I've just shown you. And for the second guess, it will output, we have to do a bit more. It will run A with switching oracles until it's finished, then rewind and then measure. in more detail. We will use the first oracle until the ith query. This will be handled with the evaluate then swap unitary. Afterwards, the extractor switches oracle access to G2. That's a finish. And after A has finished and returned its guessing bit, A gets rewound. And there we use that the adversary can be described by unitaries. And is rewound until the ith query, and then we again measure the input register. And as the guessing set will return those two values. So again, we get a tighter bound that's incomparable to the tighter bound we've seen before, but only if a reduction knows how to simulate both oracles. Now I want to briefly mention further extensions of one-way-through hiding. The first extension was given in 2019 and generalized semi-classical one-way-through hiding to the compressed oracle model. And what we do there is to puncture, what the authors do there is to puncture the oracle database with respect to relation. And the relation, you can think of it as the puncturing set. And since it's a generalization of semi-classical, the bound looks a bit similar. And again, what we do need is that the reduction knows the relation. And another generalization that was given this year is a generalization to a scenario where the reprogramming position might depend on the interaction with the adversary. And what we consider there is that the oracle gets reprogrammed on a position that we can split into two parts. Let's call them X1 and X2. And we have the adversary choose the first part, the first portion of the reprogramming position, and the game chooses the second part. And the bound we achieve is defined relative to the number of oracle queries and the maximum probability of the game choosing a particular X2. Okay, now that we've seen several versions of one-way-through hiding, I will just give a brief summary in comparison. So this is what we have seen. We have seen many different bounds, and usually the better the bound, the more additional requirements we have. So for example, we can push the Q under the square root if the reduction does know the puncturing set S. Or we can do without the Q altogether if a reduction knows both oracles, or alternatively, get rid of the square root, but at the cost of vector Q. We can also apply it to the compressed oracle, and we can also do it adaptively. Oh, question?
Several times what it means that the reduction must know G1 and G2. So it's knowledge in this case.
It must know how to simulate those two oracles consistently to the attacker.
So that means that it's just kind of oracles that usually just kind of
so usually you have a random oracle, but it has to satisfy some additional restrictions. For example, if you consider the Fujisaki-Okamoto transformation, or just the first step that we have just seen, where we de-randomize the encryption scheme, there we consider random oracle, but a reduction would have to satisfy the requirement that querying G on the challenge plaintext yields exactly the randomness that led to the ciphertext. So it's not just, no, it's applicable in the second step of the Fujisaki-Okamoto transformation, but I didn't want to also introduce this part to keep overhead. Okay, unless there are, let me just go to the slide. If there are any more questions, I'd be happy to take them, and the slides will also be available on my personal page.
Thanks.